Cool. Hi everyone, my name is Gargi, and I'm going to be talking about containers and how you can write your own container and Rust. Cool. So the talk was titled something else, but I changed it because this sounded more cool. So how I got started with Rust was I went to the Recurse Center, which is a programming community in New York, and they're the best people. And they have a lot of Rust love, and I got swept away in the Rust love. So something that they say a lot about Rust is a systems programming language. And at the time, I didn't really understand what a systems programming language meant. Because, okay, C is a systems programming language, and C++ is a systems programming language, but then why is Python not a systems programming language? So I thought we'd explore what does it even mean to be a systems programming language. So let's start with the 1970s. And in the 1970s, there was a paper called the Systems Programming Language, and it defined a systems program as an integrated set of subprograms which together forms a bigger program, and it's a complex program. So some examples of systems program by this definition would be writing a time-sharing system, or managing information, or writing a simulator. And then it goes on to define the properties of the system. So it contains the system program aims to solve a lot of sub-problems, and it's designed for production use rather than a single applications program. And then there's a certain discipline or structure in the program, both within the modules and how they communicate, and it's designed by more than one person. And yeah, so the paper, and it then defines system programming language as the goal of the systems programming language is that it can be used for more things than assembly, and then so it can be used for more things than assembly, and you're not doing bit twiddling, but you're still generating code that is better than generating code by hand. So this definition is fairly agreeable. So computers are large scale, they're long used, they're time varying. And while the paper and this definition is largely descriptive, the idea that the paper wanted to propose was fairly prescriptive. It wanted to separate the low-level language, at the time assembly, with the systems language, which was Fortran at the time. So you combine the conciseness and the readability of high-level language such as Fortran, and the language allows you to design, write, and debug systems, and with lesser time, without imposing overheads on the system resources. And then it goes on to define that in the beginning, when you wanted to program, you would have switches, so you would turn them on and off, and then you wanted to do more things. So let's say you wanted to say, give me x given that y is 10 and x is 30 into y, so what would be x? So present-day computers won't be able to understand that without systems program. So systems program like compilers or macroprocessors or operating systems were developed to make computers better adapted to the needs of their users. And then there was another paper in 1998, which was scripting higher-level programming for the 21st century. So So during the 1990s, there was a rise of scripting languages like Bash, Python, Ruby, etc. And the idea then was systems programming languages are used for writing data structures and algorithms from scratch, versus scripting languages are used for gluing programs together. So, so that is fairly agreeable. But in the 2010s, the boundaries between the systems programming language and the scripting languages blur. So Dropbox uses Python to build large-scale and scalable systems, and JavaScript is used all over the web. So there were massive engineering resources that were poured into these languages so that just-in-time compilers were developed for both static languages like Java's Hotspot or dynamic languages like Python and Python's PyPy and JavaScript's V8 compilers. So their performance was competitive with those of traditional languages like C and C++. So in 2014, there was a panel where they asked a lot of language designers, like, what does it mean to be a systems programming language in 2014? So Nico Matsakis, who's one of the creators of Rust, says, like, writing client-side applications, so you have high latency requirements and high security requirements that you don't have on the server side. So a systems programming language should allow you to do that. So by his definition, Go would not be a systems programming language. And then Henry, who wrote D, tells that if a language allows you to expose the memory allocate. If a language allows you to write a memory allocator in it, then he would say it's a systems programming language. So languages like C, C++, Rust, and D are distinguished in terms of the level of abstraction they provide you. So they expose details of underlying hardware like memory allocation and layout and fine-grained resource management. So one good question to ask if you want to say if a language is a systems programming language or not would be, if you have an efficiency problem, how much freedom do you have to solve it? So if you identify a bottleneck, is it in your power to eliminate the bottleneck by careful control over machine details, or is it not? So in the same way that static types would provide you with the confidence that, oh, I'm adding 2 integers, so the result would definitely be integers. The systems programming language would give you the confidence that this code will execute on the machine as I intended to. So systems programming today. So we should seek to understand that what are the ideas of system design we can adapt to deal with the reality of hardware. And Rust is a very good example of that because it adapts a lot of functional programming concepts and good software design ideas directly into the language in how it handles futures and how it guarantees you memory safety, etc. And if you want to throw all that away, I have a very precise definition for systems programming, which is you spend more time reading than a man page than you do reading the internet. So with that, so now we have a relatively decent idea of what it means to be a systems programming language. I want to jump on to the other part of the talk, which is like, what is even a container? So I'm sure like most people have heard about Docker. So like, what is container a process? Like, what's Docker? And are containers Docker? And so the word container doesn't mean anything super precise. So there are a lot of Linux kernel features like cgroups and namespaces and chroot that allow you to isolate processes. And like when you stable those features together, you call it a container. So these features let you pretend that you have something like a virtual machine, except that it's not a virtual machine at all. I would like to really emphasize on that. It's just processes running in the same Linux kernel. So Alice Goldfuss has a really good talk where it's like she has very prescriptive ideas about when you should and shouldn't use containers. And she says this, like, containers are processes born from turbols, anchored to namespaces and controlled by cgroups. So when you're writing a Docker file, for example, you're specifying the environment and the file structure of your application. And when you build that Docker file, you generate a turbol that's that's unzipped when you run it, and it gets unpacked, and then it's run as a process like any other process on the host. So now I'm going to be talking about the Linux kernel features that help us build a container. So one of the first features is chroot. So what chroot allows you to do is it allows you to change the root directory from the current process, and it's chosen for isolation. So you can think it of as a jail where you can't break out of the jail. So it won't access. So you would know that it won't access anything else on the machine. Sorry. So I wasn't courageous enough to live code, so hence I have this. So what I do here is a bunch of error checking, which is like set up a create a directory with whatever root path I want to create, and then bind to a new root, and then move to the new root so that I am the new root and I cannot access files outside the new root. And yeah, so the next Linux kernel feature that we care about is Linux namespaces. So Linux namespaces were inspired by Plan 9 from Bell Labs, where they used a namespace functionality very heavily. So just like chroot allows you to see any arbitrary directory in your set up any arbitrary directory as the root of your system, independent of the rest of the processes. Namespaces allow you to other aspects of the operating system to be independently modified as well. So you can have a different process tree, different networking interfaces, different mount points, different IPC communication resources, and more. So you have a PID namespace. So you can't see everything on the host. You can see only a slice of the universe. And so in a PID namespace, when you go to a different PID, when you create a new PID namespace, you become the PID one, and your children will be the subsequent processes, and all other processes outside your view, you won't be able to see them anymore. And if you are in a networking namespace, you can run any program on any port, and this won't interfere with what other programs are running on the other port. And if you have a mount namespace, you can mount different devices in your container other than what's mounted on the operating system. So, sorry. I have. So here you use something called unshare, which allows you to create a different PID namespace. So if I execute that, sorry. So if I now do I can see that I am PID 1 and PSOX is PID 2. So it allows you to isolate processes. Oh, cool. Sorry. Yep. So you can also create namespaces by a clone system call, and a namespace will be destroyed once all the processes that are in the namespace leave. And you can also enter an existing namespace by using the setNS system call. And this is all that you have to do to go to to create new namespaces. So you call unshare with a bunch of flags. So new UTS is for new UTS namespace, which is the time sharing namespace. So you can have different time zone inside your container. Then you can have a new PID namespace, and you can have an entirely new namespace. So we have namespaces, but what happens if your container uses all the resources that it can, but you don't want to allow that, and you want to limit how much memory it can use or how much CPU it can use. So for that, we have cgroups. So cgroups allow processes to be organized hierarchically. Sorry, I can't. Okay, so they allow a parent-child structure so the resources and the usage so the resource and the usage can be limited. So they're implemented by using a pseudo file system called cgroupfs, and I can sorry. So if I do sorry. So here we will see like all the C groups that we have. So we have a CPU C group where you can specify how much CPU you want to use. You have a memory C group where you can specify how much memory the container should be allowed to use. You have PIDs, which specifies how in which you can specify how much processes you should be allowed to create. So for example, if I go to PIDs.max, so it has a max, but I can say, oops, sorry. Oh, maybe I won't do that. But instead of PIDs max saying max, which is, you can say it to be 20, and then then if you start a fork bomb, you won't be able to go, you won't be able to create more processes once you reach 20. Cool. So the subgroups, so you have a parent-child relationship in C groups, so the subgroups will always inherit the limits that you set on the parent C group, and a process can be only a part of one C group, and each subsystem, like I showed you, so the memory is a subsystem which control the memory you use, the PIDs would control how much processes you can start. And then to create a C group is just it is just writing to the sysfs C group directory. So in the last two lines that are of interest, you can say that the PIDs max should just write 20, and you shouldn't be able to have more than 20 PIDs. And that's all you need to write a container. So I have a demo at the end. So I have like 75 lines of Rust code, which are all my, which is my container. So you can also do fancy things in a container, like how Docker allows you to mount a directory. But I have not done that. So I say cargo run, and it will run ls. So it will go there, it will create the C group, write 20, and then run ls on the new root. So it creates a new root, chroots into the new root, and then prints the contents of the new root. And this is the new root. Yay. Cool. That's all I have. Thank you so much.
There was one bit I didn't quite understand. You mentioned that you can have a process only be member of one C group.
Yeah.
But there was like different C groups for CPU and PIDs, and Like how can you put multiple restrictions then on a process?
So you cannot. So I guess what I meant by that, like one C group is like all the different elements that you can control. So you can have the CPU, memory usage that you can control, and then you can have like the number of processes that you can spawn inside the group. So that's all one part, and you cannot say that. So let's say if you inherit something from the parent C group, where you say the parent C group has a process ID limit of 20, and the child C group, you say you have a process limit ID of 50, it would respect the parent C group, and you won't be able to override that. Does that make sense? Cool.
I think I just misunderstood that the things that are under C groups are not
Yeah.
actually the C groups.
Yeah.
Yeah.
Hi. Does this also allow you to have a separate file system? Is this also a namespace or something?
Sorry, can you say
So
that?
I've used Docker before, and there you load your container, and then you have the Docker file system, which to me is different from the one that I was using on the host. Is this also possible in this approach with Rust?
So different file system, as in you can mount your own file system, or you
Yeah, or
copy. Yeah, so I guess I did not implement that, but you can also implement that if you wish.
and that's a namespace or something?
No, I don't think that's the namespace. Actually, I'm not sure.
All right.
Yeah, I'm sorry. Yeah.
So you focused on Rust, and I was wondering what kind of features of Rust are somehow are good for doing that. I mean, Docker is written in Go. What were the features of this programming language that is somehow good for doing the containers, or that you particularly picked up for this?
I guess my idea was to learn more Rust and not why Rust, I guess, which is a good question. You could do something very similar in Go because at the end of the day, it's using Linux abstraction. So you have like libc. So every language has like its own libc wrapped, and you can use those functions. I guess the fun thing about Rust is that if you were to do more complicated things with Docker, Rust would have, or more complicated things with writing your own container, Rust would allow you to do those safely versus it would be harder in like doing C or C++. Yep. Okay, thank you so much, everyone.